In this lecture, we will study about electromagnetic waves and spectrum. You can see here that we will learn about electromagnetics first. First, we will learn about electromagnetic waves, and then we will see their spectrum. So, what is electromagnetic wave? You can see here that electromagnetic wave do not need matter to transfer energy. Means electromagnetic waves does not require material things to transfer energy. It can propagate in free space, it can propagate in air, it can propagate in vacuum. That's why we call it that it does not require, it does not need matter to transfer energy. So basically how we generate electromagnetic waves. To generate electromagnetic waves, we will require electron in moving condition, and movement should be in such a way that there is acceleration or deceleration. How it happens? Basically, a stationary charge, stationary charge only produces electric field, electric field, electric field, while a moving charge produces electric field as well as magnetic field. So when you need electric field only, you can use stationary charge. When you need electric field as well as magnetic field, you can use a moving charge. But when you move charge with a varying speed, when there will be an acceleration or deceleration in the movement of charge, then we will get electromagnetic field. So whenever you need electromagnetic field, you need to move a charge in such a way that there is either acceleration or deceleration, or you can say that electron should be in a oscillatory motion. If an electron is in oscillatory motion, electron will travel back and forth motion with varying speed. And since electron is oscillating and that is moving back and forth with a variable speed, you will get electromagnetic wave. So in general, we can say that a moving charge produces electric field as well as magnetic field. But if the speed of movement is varying with time, then you will get electromagnetic waves. Now, electromagnetic waves, you can see that made of vibrating electrical charge. You can see that for electromagnetic wave, you need vibrating electric charges. Vibrating electric charges means electrons should move back and forth motion. That electrons should be in a variable speed. Movement should be such that electrons should move in time varying speed. If there is acceleration or deceleration, then you will be able to get electromagnetic wave. If there is no acceleration, you will not get electromagnetic wave. One more thing is that it can travel through space by transferring energy between vibrating electric and magnetic fields. A moving electron, a moving charge produces electric field as well as magnetic field. But when its speed varies, then the electric field will be changing, because the speed of electron is varying, the electric field will be changing. And if electric field is changing, a changing electric field produces a changing magnetic field. And in other words, a changing magnetic field produces a changing electric field. So electric field will give rise to magnetic field, and magnetic field will give rise to electric field. And in this way, transfer of energy from electric to magnetic and magnetic to electric will take place throughout the transfer of electromagnetic waves from space. Electromagnetic wave is transferred from transmitter to receiver. Transmitter carries an antenna and receiver also carries an antenna. An antenna is a device which converts electrical energy into electromagnetic wave. And again, at the receiver, it converts electromagnetic wave into electrical signal. So whenever you will need to transmit electromagnetic wave in space, you will be required two antennas, one at the transmitter end and another at the receiver end. At transmitter end, antenna will convert electrical energy into electromagnetic energy, and at the receiver end, antenna will convert electromagnetic energy into electrical energy. And this phenomena will keep on going until transmission and reception takes place. Now in this slide, you can see that there is a moving electric charge. You can see here that a charge is moving along this line. A charge is moving along this line, and I have told you that a moving charge produces electric field as well as magnetic field. So you can see that in this diagram, the direction of magnetic field has been given by circles. You can see here that these circles are representing direction of magnetic field. The direction of magnetic field can be calculated by right hand thumb rule. Suppose positive charge is moving in this direction, then there will be current in this direction, because movement of charge gives rise to current. If positive charge is moving from left to right, then current will flow from left to right. And to know the magnetic field, you must use right hand thumb rule. Means you have to put your thumb in this direction, and the direction of fingers will give rise to magnetic field. Means if you are keeping your right hand thumb in this direction and rotating your fingers, you will see that magnetic field is rotating in this direction. This particular direction is shown in these diagrams by these three circles. So whenever a charge will move, there will be a magnetic field and there will be a electric field, and magnetic field direction will be just in such a way that it will enclose the current, just like these three circles are enclosing the flow of current. Now, what happens when electric and magnetic field changes? A changing magnetic field creates a changing electric field. A changing magnetic field creates a changing electric field. And one example of this phenomena is a transformer. You can see that a transformer consists of two coils. In first coil, you give changing electric current, and that changing electric current will give rise to a changing magnetic field, and due to that changing magnetic field, secondary coil of the transformer will give rise to changing electric current, and in secondary coil of the transformer you will be able to get the current. So this phenomena of changing magnetic field and changing electric field is used in transformers to transmit electrical energy from one coil to another coil. The changing magnetic field is changing magnetic field creates a changing electric field, and changing electric field give rise to changing magnetic field. This particular phenomena is used at several technologies. One of them is electrical transformer. The main coil of electrical transformer gets changing electrical current and produces changing magnetic field. This changing magnetic field gives rise to changing electric field, and that changing electric field will give rise to electrical current in secondary coil of the transformer, and the reverse of this operation also takes place. Now in this slide you can see that there are two waves. One is shown in blue color and another is shown in orange color. Blue color is for magnetic field and orange color is for electric field. You can see that electric and magnetic field both are perpendicular to each other, and both are propagating in direction perpendicular to each other. You can see here that electric field is given by this orange colored wave, and magnetic field is given by this blue colored wave, and both are perpendicular to each other, and they both are propagating in this direction. This is perpendicular to both electric field as well as magnetic field. Direction of propagation of electromagnetic wave is governed by right hand rule. How it will give rise to this direction? Electric field is in this direction. As you can see that electric field is in this direction, and magnetic field is in this direction. Magnetic field is in this direction. So to get the direction of propagation of electromagnetic wave, you will use right hand rule in such a way that put your right hand on the electric field line and rotate your fingers towards magnetic field. Rotate your fingers towards magnetic field. Then direction of thumb will give rise to the direction of propagation of electromagnetic wave. This is called right hand rule. You put your fingers in the direction of electric field. You put your palm in the direction of electric field and rotate fingers towards the magnetic field. Direction of thumb will give rise to the direction of propagation of electromagnetic wave. So in this way, this is the electric field, this is the magnetic field. If you will rotate your fingers from electric field towards the magnetic field, direction of propagation will be this one. So you can see here that electric field and magnetic field both remain perpendicular to each other, and they travel perpendicular to both. You can see here also, when a electric charge vibrates, when an electric charge vibrates, the electric field around it changes, creating a changing magnetic field. A changing electric field produces a changing magnetic field. In other words, you can say that if you are if you are moving a charge in such a way that its speed varies, its speed varies means electric charge is vibrating. Electric charge is oscillating in back and forth motion, and if electric charge is oscillating in back and forth motion, you will get a changing electric field, and changing electric field will give rise to changing magnetic field, and in such a way electromagnetic wave will be generated. This is the electromagnetic wave where electric field as well as magnetic field both are being produced with the help of vibrating electric charge. Vibrating electric charge may also be called as oscillating electric charge. The peak to peak distance between any wave will be called as wavelength, and wavelength is particularly dependent upon the frequency. The wavelength and frequencies are related by the formula lambda equals to C upon F. If frequency is high, wavelength will be low. If frequency is low, wavelength will be high. Means peak to peak distance will be low if frequency is high, and peak to peak distance will be high if frequency is low. In this diagram, you can see that magnetic and electric fields create each other again and again, and this process will keep on going, and electromagnetic wave will propagate along the space. This is again the same thing. The electromagnetic wave travels in all directions. Electromagnetic wave actually propagates in all directions, and for the sake of convenience, only one direction is shown here. It does not mean that electric and magnetic field will give rise to propagation of electromagnetic wave in a single direction. Electromagnetic wave can propagate in all the direction, but wherever it propagates, the electric field and magnetic field will be perpendicular to the direction of propagation as well as perpendicular to each other. And since electric field and magnetic field both are perpendicular to each other, electric field is in this direction, magnetic field is in this direction, the angle between these two waves is 90 degree, they will be called as transverse wave. Transverse wave means electric field component and magnetic field components will be perpendicular to each other. Now, properties of electromagnetic waves. All matters contain charged particles. We all know that any material in the universe consists of electrons and protons, positive charges and negative charges. There is no material in the universe which does not contain any charged particle. And these electrons will keep on moving within the material. So, if charges are moving, there will be electric field as well as magnetic field. I have already told you that a stationary charge produces electric field. A moving charge will give rise to electric field as well as magnetic field. And if the speed of movement is varying, it will give rise to electromagnetic wave. So, since in universe every material consists of electrons, and electrons keep on moving within the material, there will be a movement of electrons, and this movement of electrons are random. They don't vary with the constant speed. They don't move with the constant speed, so speed is also varying, so there will be electromagnetic wave. So all the objects of the universe emit certain amount of electromagnetic waves. The wavelengths and temperature are dependent. If the temperature of a material in the universe is high, then wavelength will be small, and if temperature is small, if the temperature is low, the wavelength emitted by the that particular material will be large. Now, every electromagnetic wave carry some energy in the form of electromagnetic radiant energy. For example, sunlight is an electromagnetic wave, and it consists of radiant energy. Now, what is the speed of electromagnetic wave? A electromagnetic wave can travel with the speed of 3 lakh km per second. Means electromagnetic wave propagates with very high speed. Its speed is 3 lakh per kilometer in space. Its speed is less than 3 lakh km per second in the air. Air is similar to space, but there are some particles in the air, and therefore electromagnetic wave will travel into the air with a speed nearly equal to 3 lakh km per second, but not exactly equal to 3 lakh km per second. 3 lakh km per second speed is in the space. Speed in the air will be slightly lower than 3 lakh km per second. Similarly, electromagnetic waves will travel with the water with a very different speed. You can see that speed of electromagnetic wave in the water is 2 lakh 26 km per second, while speed of electromagnetic wave in the air is around 3 lakh km per second. In the water it is 2 lakh 26 km per second. In the glass it is 2 lakh km per second, and in the diamond it is just 1 lakh 24 km per second. So you can see that as the density of the material is increasing, as the density of material is increasing, the speed of the electromagnetic wave is decreasing. So electromagnetic waves usually travel slowest in the solids and fastest in the gases. Electromagnetic wave is traveling faster in the vacuum and in the air, and slow in the diamond. So electromagnetic waves will travel slower in the solids and faster in the air or vacuum. Fastest in the vacuum and slowest in the solid. Now, what is the wavelength and frequency of an antenna? The wavelength is basically the peak to peak distance. Suppose if a wave is like this, then the peak to peak distance from this point to this point, the distance is called as wavelength, and this is also called as crest to crest distance. Wavelength is basically peak to peak distance of a wave, and inverse of wavelength frequency is given by f equals to c by lambda. If you want to calculate frequency, then it will be given by c upon lambda, where c is the speed of electromagnetic wave in space. So you can see the relationship between wavelength and frequency. This is frequency, this is wavelength. Frequency and wavelength are inversely proportional to each other. Frequency is number of wavelengths that pass a given point in 1 second. Means wavelengths per second will be called as frequency. Frequency can also be defined as frequency equals to wavelength per second. Number of wavelengths that pass a given point in 1 second will be called as frequency, and lambda and frequency are related by lambda equals to c upon f. As the frequency increases, wavelength decreases. As the frequency increases, wavelength becomes smaller. As the frequency increases, wavelength will become smaller. The reason behind this is that wavelength and frequency are inversely proportional to each other. F equals to c by lambda. F equals to c by lambda. As the wavelength increases, as the wavelength will increase, as the wavelength increases, frequency will decrease. Or you can say that lambda equals to c by f. As the frequency increases, wavelength will decrease. The increase in frequency will decrease the wavelength. Can a wave be a particle? In 1987, Heinrich Hertz discovered that when sunlight was incident upon a metal, it ejected electrons. Means when he did his experiment, he used sunlight and incident the sunlight on the metal surface. After incidenting, he found that a electron is ejecting out of the metallic surface. So whenever you need to eject electrons from a metal, you can use sunlight, and after incidenting sunlight, electron will be ejected. This experiment was performed by Heinrich, and he also told that this ejection of electrons was dependent upon frequency rather than amplitude. Means high frequency signals, high frequency electromagnetic waves caused more electrons to be ejected than low frequency electromagnetic waves. Means high frequency electromagnetic waves will give rise to more electrons as compared to low frequency electromagnetic waves, and it was independent of the amplitude of the light. Means higher the frequency, higher will be the ejection, lower the frequency, lower will be the ejection. Higher the amplitude does not mean higher ejection of the electrons. This theorem was further proved by Albert Einstein, and Albert Einstein told that a wave can behave as a particle when a light is incident upon a metallic surface, it ejects electron, and that electron will have some energy, and that particular particle, that particular ejected electron having some energy will be called as photon. Photon has been told as a particle by the Albert Einstein, and its frequency, its energy depends upon the frequency. If higher frequency signal is incident upon the material, the ejected photon will have higher energy, and if lower frequency electromagnetic wave was incident, the photon energy will be low. Means photon energy was dependent upon the frequency of the incident wave. Here was here an experiment was shown. You can see here that electrons are being fired through two slits. Slit 1 is this and slit 2 is this. When electrons are being fired, it is accumulating on this slit, just like waves interfere with each other. Means it is proving the wave nature of the particle. Electrons are being fired through these slots, these openings. These openings will be called as slits. Electrons are being fired through these two openings, and its behavior is being recorded on a screen. It was found that the fired electron were in such a way as different electromagnetic waves interfere with each other. Electrons fired at two slits actually form an interference pattern similar to pattern made by waves. So this particular phenomena proves the wave nature of a particle. So a wave is a particle as well as a particle can be a wave. In this particular picture, you can see that electromagnetic wave is being incident upon two slits. Slit 1 is this, slit 2 is this, and after passing through this slit, the particle is behaving like a wave. Electrons fired at two slits actually form an interference pattern similar to patterns made by waves. These two lines proves that particle can be of wave nature. So what is electromagnetic wave? How they are formed? Waves made by vibrating electron. I have told you that a vibrating electron or an oscillating electron or an electron which is moving with the varying speed will give rise to electromagnetic waves, and they will travel through space without any material requirement. So electromagnetic waves are generated using oscillating electron. Electromagnetic waves can be generated by using oscillating electrons. You just need to oscillate electrons and you will get the electromagnetic waves. Oscillating electrons will be also called as vibrating electrons or vibrating electric charges. You will get electromagnetic waves, and these vibrating electrons, these oscillating electrons will give rise to electromagnetic waves in which electric field and magnetic field both will be perpendicular to each other. Electric field and magnetic field both will be perpendicular to each other, and they will propagate perpendicular to both. Means the angle between this electric field and direction of propagation of electromagnetic wave will be 90 degree. The angle between magnetic field and direction of propagation of electromagnetic wave will again be 90 degree. And this direction is calculated by using right hand thumb rule. Means you will use right hand rule. Means you will put your hand in the direction of electric field and rotate your fingers in the direction of magnetic field. Thumb will give rise to the direction of propagation of electromagnetic wave. So this, you can see that these are transverse electromagnetic field. Transverse electromagnetic wave. So you can see electric field and magnetic field both are perpendicular to each other, and they are propagating perpendicular to each other. So they are of transverse electromagnetic nature, and that's why the kind of wave generated will be transverse with alternating electric and magnetic fields. They will behave as a particle and they will behave as a wave. Means these vibrating electrons, these oscillatory electrons will produce electromagnetic wave, and these electromagnetic waves will sometimes behave as a wave, sometimes behave as a particle. Now electromagnetic spectrum. Frequencies are basically called as electromagnetic spectrum. Means range of frequencies over which you are using electromagnetic wave will be called as electromagnetic spectrum, and different electromagnetic spectrums will be used for different applications. Frequency range. Electromagnetic spectrum means frequency range of frequency used for a particular application. Different parts interact with matter in different ways. The one human eye can see are called visible light. You can see that there are frequencies from 0 to infinite in the universe. The one human eyes can see, the frequencies which human eyes can see are called visible light. A small part of the whole spectrum is visible light. Visible light is the small part of the whole spectrum. There are signals of zero frequency up till infinite frequency. Of those, only a few frequency components are seen by humans, and that range of frequency will be called as visible light. In this diagram, frequency spectrum have been shown. Range of frequencies for different applications, for example, radio waves, microwaves, infrared, X-rays have been shown. You can see that as the wavelength is decreasing from higher to lower in this direction. Frequency is increasing in this direction. As the wavelength is decreasing, frequency is increasing. Higher the wavelength, lower will be the frequency. See, in this diagram, wavelength is decreasing, and in this diagram, wavelength is frequency is increasing. The reason behind this is that wavelength and frequency both are inversely proportional to each other. Lambda equals to c upon f. If you will plot wavelength, then frequency will be just opposite of wavelength. In this diagram, the wavelength is decreasing. You can see here that 10 power 3, 10 power 2, 10 power 1, then 1, then minus sign in the power is appearing, and it is keep going till minus 20, minus 12, 10 power minus 12. While in this side you can see that frequency is appearing in the positive powers. 10 to the power 17, 10 power 16, 10 power 15, 10 power 23. These are positive powers, and you can see that when the wavelength is minimum, frequency is maximum. Antennas are the devices which can detect electromagnetic wave. Basically, I told you that antenna is a transducer. Antenna is a transducer which converts electrical energy into electromagnetic energy, as well as it converts electromagnetic energy into electrical energy. It will be used to detect electromagnetic waves, which will be in the form of frequencies. Devices that detect frequencies are antennas. Antenna is a transducer. Antenna is made of metallic wires, metallic sheets, and they are able to detect radio waves. They will be able to receive and transmit electromagnetic waves. Radio waves are low frequency electromagnetic waves with wavelength longer than 1 mm. Means radio waves are the waves whose wavelength is longer than 1 mm. Wavelength will be just lambda equals to c by f. Since c is in kilometer, 3 into 10 power 8 kilometer per second, and f is in the hertz, you will get lambda, whose unit will be in terms of length. So you will further convert it into the mm to get the wavelength. So the radio waves has wavelength longer than 1 mm. Antenna of a radio detects radio waves, and these waves must be turned into sound waves by a radio before you can hear them. So when electromagnetic waves are received from the space, these electromagnetic radio waves are converted into sound by radio stations, and that sound can be heard by the human beings. Now, what is microwave? Microwave is a high frequency signal. It is the frequency above greater than 1 gigahertz. Since frequency is greater than 1 gigahertz, its wavelength will be smaller than 30 centimeter. So you can see that the radio waves whose wavelength is shorter than 30 centimeter will come under microwave signals. Microwave signals are those signals whose frequency is greater than 1 gigahertz, or you can say that their wavelength is less than 30 centimeter. Wavelength and frequencies are related by lambda equals to c by f. So you can easily convert wavelength into frequency and frequency into wavelength. Cell phones and satellite use cell phones and satellites use microwaves between 1 centimeter and 20 centimeter. Means the radio frequency having wavelength 1 centimeter and 20 centimeter and in between will be used for communication in satellites and cell phones. Also, microwave ovens use microwave signals. Microwave ovens used in kitchens of the households. In this particular oven, basically high frequency signals cause water molecules to vibrate, and vibrating water molecules due to friction give rise to heat, and that heat is used to cook the food. So in this way, microwave ovens work. Electric field will give rise to the vibration of water molecules, and water molecules due to friction will give rise to heat, and that heat will cook the food. So this particular microwave signal is used in microwave ovens, is used in phones, used in satellites, and these are the applications of microwave signals, which whose range is greater than 1 gigahertz in terms of frequency, and less than 30 centimeter in terms of wavelength, and that should be less than 30 centimeter to be called it as a microwave. Radar is a device which is used for positioning and speed calculation of objects moving in space, and these devices also use radio frequencies. Radio waves are used in radars also. Radars are used basically to find out the position and speed of the objects in space. For example, if you want to check the speed of an aeroplane, you can use a radar to find the speed. MRI is another example of radio waves. In this, basically, receiver is used with the help of radio waves to create a map of body's tissue, and body's tissue give an information about the present disease in the human being. So MRI uses radio frequencies, and in this radio wave, basically we create body's tissue map of the body's tissue to diagnose the disease. This is again the application of microwave frequencies. Infrared frequencies are those frequencies which have wavelength in between 1 millimeter and 750 billionth of the meter. If the wavelength lies in this region, then that kind of wave will be called as infrared, and it is used particularly in remote remotes of the television and other devices. If remotes emit infrared waves. So application of red waves are in remotes. Application of microwaves are in microwave oven. Another category of electromagnetic wave is visible light, and when you see different colors, it does mean that there are different wavelengths. Shorter wavelength appears blue, longer wavelength appears red, and if all the wavelengths are getting mixed, then that will appear as a white. So you know that red signal has the highest wavelength and blue has the lowest wavelength. Based on the wavelength, there are several categories of spectrum. Very long wave radio, very long wave radio will be used for communication within the submarine. Then long and medium and short wave radio. Long, medium and short means here wavelength is long, short and medium. Means based on the wavelength, these radio waves have been classified. Electromagnetic waves with wavelengths from about 400 billions to 10 billions of a meter will come under ultraviolet waves. Ultraviolet waves will have wavelength in this range 400 billions of a meter to 10 billions of a meter. If wavelength of electromagnetic wave is in this region, then that particular electromagnetic wave will be called as ultraviolet wave. Ultraviolet wave have enough energy to enter skin cells, means it can enter into the body of human being, and it can cause cancer if used for prolonged period. So human beings are sensitive to ultraviolet waves, and they should avoid exposure to UV rays because they might cause skin cancer. These are the applications of different frequencies. At low frequency, you are using your laptop. At radio frequencies, you are using your mobile. At infrared, you are using your remote. And at the X-rays, you are using X-ray films for the diagnosis of several diseases, just like tuberculosis and other diseases can be identified with the help of X-rays. So different frequencies are having different application, and all these frequencies are just electromagnetic wave. As the frequency is increasing, you can see that wavelength is decreasing. Here the wavelength is peak to peak distance is very high because frequency is low, and at this particular moment peak to peak distance is in the means very small because frequency is very high. So if frequency is high, wavelength will be low. If wavelength is high, frequency will be low. So this is the relationship between frequency and wavelength, and these are the applications of different frequencies. This is again frequency chart showing different wavelength and different frequencies, and accordingly they will be called as radio frequency, micro frequency, X-ray, and gamma rays. This is the frequency chart. As you can see here that as the wavelength is decreasing, you can say that frequency is increasing from this side to this side. This side is having high frequency, this side is having lower frequency. Now radio transmission. In radio transmission, radio stations change sound to electromagnetic waves. At radio stations, sound wave will be converted into electromagnetic waves, and then it will be transmitted into the space. At the receiver end, those electromagnetic waves will be again converted into the sound wave. So this phenomena takes place in the radio transmission. What is AM transmission? When the information signal is sent through the electromagnetic wave in such a way that the carrier signal, which is the electromagnetic wave, the carrier signal is affected by message signal in such a way that amplitude of the carrier signal is changing as per the message signal, then that particular kind of wave will be called as amplitude modulated radio wave. Amplitude of the carrier signal will be changed according to the information signal. Amplitude of the electromagnetic wave will change according to the information signal amplitude. Then that kind of radio will be called as AM radio. And in amplitude modulated AM radio, frequency range lies between 540 kilohertz to 16,000 kilohertz, usually listed in the kilohertz. So what is AM? AM means amplitude modulated. Amplitude modulated means amplitude of the carrier signal is changed according to the information signal. Other than AM signal is FM signal. In FM signal, frequency of the carrier signal is modulated according to the information signal. That will be called FM signal. Next one is FM radio. In this particular technology, amplitude of the carrier signal is not changed, but instead here frequency of the carrier signal is changed according to the amplitude of the message signal. If this is the message signal, at this particular point the carrier signal will have maximum frequency, and at this particular point the carrier signal will have minimum frequency, while transmission between transmitter and reception is taking place.